Just like we did for the flow with friction, we are able to apply the mathematical expressions that we got for Rayleigh flow or flow with heat addition and use it to compute variables downstream in the pipe if we are given inlet conditions. Let's show that through this example. Let's consider flow through a pipe where the inlet Mach number is given to be 3.5, temperature is 600 Kelvin at the inlet, and a constant heating per unit mass of 5 times 10 to the 5 joules per kilogram is applied on the fluid in the pipe. We are asked to calculate the Mach number at the exit, the temperature at the exit, and the ratio of stagnation pressure at the exit to that at the inlet. We're told to assume that the ratio of specific heats gamma is 1.4 and the Cp or heat capacity of air is 1005 joules per kg Kelvin. Alright, the first thing we'll aim to do is an energy balance. To do that, we need stagnation temperatures. So as a first step, we'll try to compute the stagnation temperature at the inlet for whatever information is given at the inlet. So let's first compute T over T naught, and for this we'll be using the isentropic flow relations that you've learned previously. And instead of doing that calculation by hand, I'm going to use this excellent compressible flow calculator developed by Professor Davenport and co-workers from the Department of Aerospace and Ocean Engineering at Virginia Tech. So let's get to the calculator. Alright, so I've already put up the Mach number here at the inlet as 3.5, and when I say calculate, and I've used the gamma 1.4 that we have been asked to use, when I hit calculate, you can see that the calculator does an isentropic flow calculation and gives us T over T naught, which has this value. Alright, when we come back, we're going to insert that value for T over T naught, and since we have a value for T at the inlet, using that we should be able to compute the stagnation temperature T naught as T naught in equals T at the inlet 600 divided by the ratio T over T naught, which comes out to be 2070 Kelvin. Next, as I said before, we'll do an energy balance from which we want to calculate the exit stagnation temperature. So clearly the heat that we are adding to the flow needs to change the stagnation enthalpy of the fluid. Therefore Cp times Q should be equal to Cp times T naught exit minus T in, from which we can rearrange terms and express T naught exit as Q over Cp plus T naught in. Substituting numbers, since we have values for Q, Cp and T naught in, we get T naught exit should be 2567.5. I'm not going to do that calculation for you. I hope that you can just work it out for yourself. Next, once we have T naught exit, we can start looking for the ratio T naught exit over T naught stagnation, and we can do that by rearranging terms. So we'll write T naught exit by T naught star should be equal to T naught exit by T naught in multiplied by T naught in by T naught star. So clearly the T naught in and T naught in will cancel, giving us back T naught exit by T naught star. Now the reason we're doing ratio to star quantities, that is where the flow chokes downstream, we know that we denote that by the star. The reason for that is we're going to go back and use Rayleigh flow relations in just a moment. How do we do that? Alright, so T naught exit over T naught in, that we can compute because we have both T naught exit calculated here as well as T naught in calculated there. So we can substitute directly for those. Now for T naught in by T naught star, we have the Mach number at the inlet and we know this is Rayleigh flow. Therefore we can go back to the calculator, scroll down to where Rayleigh flow calculations are performed, which is over here. And we can say the Mach number at our inlet is 3.5 in this problem. Hit calculate and we see that T naught over T naught star has this value 0.6158. So I'm going to copy that, take it back, paste it in for T naught over T naught star, T naught in over T naught star, and then I can work out T naught exit over T naught star just by doing this algebraic calculation. That gives us 0.7638 for T naught exit over T naught star. Now the next step should also be obvious. Just like we did with this variable, we said since we know Mach number, we can apply the Rayleigh flow relations directly. We can do the same thing and apply Rayleigh flow relations again, and just let me just remind you what that is in a second. So what we're going to do is take this value of T naught exit over T naught star and use that to compute the Mach number. And we know that behind the scenes, this compressible flow calculator, when it does Rayleigh flow calculations, is using this mathematical expression that we derived in our theory part of this course. So we know that T naught over T naught star can be expressed as a function of Mach number and gamma. And in this equation, if we now tell the calculator that this is known, T naught over T naught star is this value, we are asking it to compute the Mach number based on this equation. And that's what the calculator is doing. So let's go do that. To do that, I need to grab the value 0.7638, go back into the calculator. Alright, so actually I don't have that value here, so let me just compute that, which is easily done, as we know the ratio T naught 2 was 2567.5, that's what I had calculated previously, divided by T naught in 2070 multiplied by the ratio T naught into T naught star. And if I hit this, I get my 0.7638, which is T naught exit over T naught star. Let me grab that, go back to the Rayleigh flow calculator, paste that in, except now I'm going to say this is equal to T naught over T naught star for supersonic. Notice that, like with the Rayleigh flow case, there's an option always of subsonic and supersonic. Since we started with the supersonic Mach number at the inlet, we know that we can only reach, at the least we can reach Mach 1 and no Mach number less than that for the case of adding heat. Therefore, we have to choose supersonic as the option here. So when we do that and say calculate, again the calculator uses Rayleigh flow expressions and calculates all the possible ratios that we want. So from this we get the Mach number to be 2.156, so we can directly use that. We can also grab P naught over P naught star, since we'll be asked to calculate P naught at the exit divided by P naught at the inlet. So let's grab these two numbers and store them in our main sheet. So Mach number has been stored, and I will get to the pressure in a second. So the next thing we are asked to calculate is T exit. To do T exit, we're going to say that's equal to T naught exit times T exit by T naught exit. T naught exit we just computed. T exit over T naught exit we can get again from isentropic flow relations. And to do that we need the Mach number at the exit, which we just calculated. So I will go back to the calculator and say, since I have the Mach number, I can use that, go back to the isentropic flow calculator and say now the Mach number at the exit is this value, hit enter. Once I calculate that, I get T over T naught to be 0.518. This is at the exit. So coming back, I've used that number here. So T naught exit times this ratio gives us 1330.4 Kelvin. So the exit temperature has risen from 600 Kelvin that it was at the inlet to 1330.4 due to heat addition. Alright, so now that we have T exit calculated, the last thing we need to do is compute the ratio of stagnation pressure of exit to that at the inlet. Alright, to do that, let's write out the expression first. P naught exit by P naught in equals P naught exit multiply and divide by P naught star, P naught exit by P naught star over P naught in. Clearly this can be obtained as a function of the exit Mach number using Rayleigh flow relations. This can be obtained as a function of inlet Mach number using Rayleigh flow relations. When we computed Mach number at the exit, I pointed out that we can grab the P naught exit by P naught star, which is 1.68596. I've used that there. And similarly, when we can go back to the calculator and see that if I apply Mach number to be 3.5 for the case of Rayleigh flow and calculated, I can see that the P naught over P naught star at the inlet should be this value, 5.328. So let me go back and substitute that in. Substituting these two, we get this ratio to be 0.32. That is 68% of the pressure that we started with, the stagnation pressure that we started with, has been dropped. due to the heat addition. So this is a significant pressure loss compared to what happened in the case of flow with friction.